Alright, welcome to the Grauer Physics video for Chapter 22. This one's going to be about electrical current and resistance. So we're going to transition from what we learned in Chapters 20 and 21, which was all with, for the most part, stationary charges, and looking at the forces on them, the electric fields generated, the differences in voltage between different areas based on where you are around a charge, and the amount of energy gained or lost by charges as they moved through a stationary configuration. So we're going to switch now and look at what happens when you connect a whole circuit together and you have charge continuously flowing through the wires in the circuit, which is going to deliver energy from some source to some load, which is typically a light bulb or an electrical device that's plugged into your wall. Okay, so first we need to define what is current. Current is a flow of anything, really. So the two that you're familiar with, or the one that you're familiar with, should be a current in a river, for example, which is a flow of water. So this is called electrical current, which is a flow of electrical charges. And so the rate of flow is the amount of stuff moving per second. So in this case, it's charges. So the amount of charge, it's delta Q because it's the delta is kind of misguided in my mind. It's the amount of charge passing per some unit of time. So you could look at the total charge passing and the total amount of time. And typically you'll measure this in coulombs per second. So how many coulombs of charge pass by a given point in every second. And the symbol we use is capital I. I will write my capital I's like this, but the computer doesn't put the tops on them. So when I write it, I'll do capital I for current. It's annoying that we don't use C, but C is already coulombs and a bunch of other stuff. So that's just how it is. So as we said before, the charges are typically going to be electrons. Alright, so real life versus math. Interestingly enough, when they were originally kind of discovering electricity and making the conventions for all this kind of stuff, they didn't have any understanding of the internal structure of an atom, really. And so they didn't know what it was that was moving or carrying the charge. And so mathematically, it makes more sense to think about positive charges moving around. And so all the structure of how circuits work and how charges are moved around was based on defining the charge carrier, the little particle that moves around, as being positive. And then it turns out later on, obviously, we've learned a lot more since then, and we've learned that it's actually the negative electron that's the thing that's moving around. So what's really happening and how we're going to solve the problems is going to be different. What we're going to do when we're solving problems is we're going to just pretend that there are positive charges moving out of the positive terminal of the battery and into the negative terminal. But what's really happening is there are actually negative electrons moving out of the negative terminal the other way around. And it doesn't matter because a positive charge moving in the positive direction or a negative charge moving in the opposite direction both end up mathematically with the same result. So it will work. And in your head you just have to remember that it's actually electrons moving the other way. Even though we say a current of, say, 5 amps is going this way, well, there's nothing actually moving that way. Instead, the negatives are moving the other way. Okay, so conservation of charge, we already said that charge is conserved, and since all current is a flow of charges, the charges are conserved, and therefore the flow of charges is also conserved. So if you have a bunch of current running through a circuit, it can't just disappear or go somewhere. Kind of like a river. If you have a whole bunch of water traveling through, a canal or a river, that water, at any given point, the amount in has to equal the amount out, otherwise you're going to have a buildup of water. Same thing for a circuit. If you have a certain amount of charge coming in or current coming in, you have to have the same amount of current coming out. Otherwise, you're going to have a buildup of charge in some spot. And the only place that you can really have a buildup of charge would be like a capacitor or something like that. But even then, what you're building up on a capacitor is equal amounts of positive and negative. So the net charge built up is actually 0. So even with a circuit with a capacitor, the current goes straight through, and whatever current is coming in equals the current coming out. So there's two ways that we say this. One is along a wire with no branches. That means it doesn't split off at all. The current is the same everywhere along that wire. And then when you do get to a branch, so a branch would be like you have a circuit coming in here, and then it branches off and it goes two different directions. So the total current into the branch, so the total current coming in here, that would be your total current in, has to equal the total of both of these guys combined coming out. And this should make common sense, just like, a water or a river branching off into two rivers. So I have a little picture. This is a top-down view of, I think, a delta of some sort. But you've got some kind of thick river coming in here, and then, it branches off. Some goes this way, some goes this way. So the total water coming out of these different branches equals the total water coming in from this bigger branch. And then, you know, each of these guys might sub-branch even farther into 3 paths. You know, and then you just trace it all the way down. So at any given branch here and here, the total water in equals the total water out. Same thing for current. Okay, so here's a little sample problem. If you have 10 amps, I think I might have forgotten to mention this, that the unit of current, I, is the variable for current, and the unit is an amp. It's actually an ampere, named after a probably French scientist, but we just call it an amp, and the symbol is A. So 10 amps coming in. If 5 of it goes this way, you can simply deduce that 5 amps must have gone this way. So I2 has to be 5 amps. Okay. From here we had 5 amps coming in at this branch point. 3 amps went this way, so how much must have gone this way? Must have been 2 amps. Okay. Now look over here. We had 3 amps coming in and an unknown amount coming in, and they have to come together and give us 4 amps. So 3 amps plus something equals 4, so this one is 1 amp. Okay, now look here, I had 5 amps coming in, 1 amp went this way, which means 4 amps went this way. And a double check, total coming in on this side, 10 amps, total coming out on this side, 2 plus 4 plus 4, 10 amps. So the current in equals the current out. Hopefully this example makes sense and matches your intuition and isn't too difficult. In a lot of cases, the math will be this easy. You'll just have kind of simple numbers and they're breaking apart into different amounts when you have more complicated circuits. Okay, so we're going to be drawing lots of circuit diagrams, which is going to basically show how batteries are connected to all the things that you want to connect to them. So it could be light bulbs or resistors. Pretty much any electrical device is going to have some kind of resistance, and you're going to use that in your circuit diagram. So light bulbs, I have to admit, a lot of times I just draw them as a resistor, same as this. Because a light bulb, it has a resistor in it. That's how it works. So to me, resistor and light bulb, I just draw the same way. And then I usually label them like, you know, R sub light, if it's a light bulb. Or if it's a toaster oven, I put R sub toaster, or whatever the resistance is. And we'll get to what resistance is in just a second. Second thing I want to notate is that a battery, a lot of times it does it a long line, short line, long line, short line. But you can also just do one long line and one short line. You don't have to do the double. And if they do the double, it doesn't necessarily mean that there's 2 batteries. It just, that's a voltage source. Also for a battery, the longer side is always positive and the shorter side is always negative. You don't have to label them, but in the beginning, if it will help you remember, I encourage you to label the longer side positive and the shorter side negative. Wires, you want to keep your circuit diagrams drawn with all straight lines and all perpendicular to each other if possible. So your diagrams should pretty much be rectangles or squares. You don't want to have some curly things like this, and oh, here's my battery, and then, oh, like, here's my resistor. Like, that's a terrible circuit diagram. How it should be, the right way to draw that would be, here's a battery, here's a resistor, just like that. So this is a good way to do it. This is a bad way to do it, if you have one battery hooked up with one resistor or light bulb. To draw a junction of 2 wires, you just draw them touching each other. Capacitors, we won't deal with too much, but if we get to them, it's 2 parallel lines, typically because they're a parallel plate capacitor. And then a little switch, if you want to show something that can be opened or closed, you just draw it like this. So circuit diagram's not too difficult to draw. We'll do lots of examples, probably in this video as well as in class. Okay. This is not a circuit diagram. This is what I would call a picture or a sketch. Just re-emphasizing the idea that what's happening in real life is a little bit different than how we calculate things. So the direction of positive current comes out the positive side this way, around through the light bulb, and back in the negative side. Remember, positive flow away from positive towards negative. But remember, what's really happening is that you have electrons coming out the negative side and going the opposite direction and then traveling back into the positive side. So again, it doesn't matter, it doesn't change calculations, doesn't even change really what happens in real life, but it does change how we think about it. Okay, so while I'm on this slide, I guess I want to mention real quick, how does a light bulb work? There's 2 wires here, and they're connected by what's called the filament. So one of these wires is connected to the side, and it's not drawn well. It looks like they touch each other. They don't touch each other. One of them is connecting to the bottom here. Okay, so when this, well, I probably should have drawn it a different way, but whatever. When the charges come in here, they go in this side, say, which means they go up here. When they go through the filament, that filament is where they actually give off their energy and therefore produce light. Then they go back down this side and then out this side. And this side, if you want to visualize it, is kind of wrapped around to here, and then they move on their merry way. The entire outer casing is touching this edge. And so in this filament right here, what is a very thin tungsten wire, and it has high resistance. So when the charges go through, because of the high resistance, it heats up the filament, and it gets so hot that it glows, and that produces light. So that's your typical incandescent tungsten filament light bulb. All it really is a small piece of metal that's getting so hot that it glows. So it's actually quite simple. Okay. All right. So now we'll talk about what is this resistance that causes the light bulb to glow, or things to lose energy, or things like that. So any material, if you have charges traveling through it, they're going to resist the flow of those charges, because it's a physical, object, and you've got physical particles traveling through it. Imagine a really crowded room, and you're trying to race your way through. You're going to bump into people, and it's going to take energy or work for you to get through that obstacle. And the amount of energy or work that is required depends on the type of material that you're trying to get through, just like it would depend if it was a crowded room or a not that crowded room. So when the charges travel through the material, they collide with the atoms that the material is made of. And different materials have different densities of atoms and structures, and I mean, it's not necessarily a physical collision, but when I say collide, I guess I should say the electron interacts with the atoms as it passes by. It might be attracted to them or repelled from them. It might gain energy, it might lose energy based on its proximity to the nucleus and things like that. And all that causes friction, so to speak, between the particles, which causes the materials to heat up. They get agitated, they collide, etc. And so the material will heat up, and the energy of the particle will decrease. Now it's important to note that what's decreasing in the electron that's traveling through is its potential energy, not its kinetic energy. That's really important to remember. It's not, the electron doesn't start off going really fast and then gradually slow down as it snakes its way through some resistor. It's going pretty much the same speed the whole time, but it's losing potential energy rather than kinetic energy. Okay? So a material has two properties. One is called its resistivity, which is the symbol rho. I don't think this is in this slide, but it's important to tell you. So the resistivity is a property of the material itself. And so it's going to be constant for any given type of material. So resistivity of copper or silver or tungsten or things like that. So different materials have different resistivities. Material. Okay, but then once you've determined what material you're going to make this resistance out of, it also depends on how long the wire is and how big around it is. So the formula for resistance is the resistivity times length divided by cross-sectional area. So this is length, and this is cross-section area. So what that means is if you have a really long wire, high length, you're going to have a high resistance, which means it takes a lot of energy to get through it because it's so long. I mean, that should make sense. Cross-sectional area is how big around it is. So if you have a big cross-sectional area, then it's going to actually have a low resistance, which also makes sense. If you have a very large space that you're traveling through, it's going to be a lot easier to get through than if you're constrained to a very narrow space that you're traveling through. So you should write this down, that rho is resistivity, and also that resistance is rho L over A. Resistivity is constant for a given material, so it's constant for a given material, but not constant overall. Different materials have different values. And then every individual resistor will have completely different resistances based on its length, its cross-sectional area, and what material it's made out of. Okay? So we have Ohm's law, the most important equation from this whole chapter, perhaps the most important equation in the whole unit. This is going to be the equation that we use to analyze almost everything that's happening in circuits. So it's the relationship between the change in voltage for any object in your circuit to the current going through the object to the resistance of the object. So it allows you to figure out how much energy is being spent in a light bulb. It allows you to figure out how much current is going to be drawn by a given circuit, so that way you can figure out what type of fuse you need to protect yourself from fire damage, what kind of circuit breakers you need in your house, all that kind of stuff. So it's very useful for calculating the voltage or the current or the resistance, given that you know two of the other ones. Your units for R, which is your resistance, are called ohms, which is the Greek capital letter omega. And the unit, if you divide both sides by I, you get volts divided by current, which is amps. So volts divided by amps are ohms. It's fun to say ohms. So the drop in voltage, and remember voltage is proportional to energy. So the drop in voltage or energy is proportional to the amount of current going through and the amount of resistance that you encounter. So the more current that you have going through, that means there's more charges passing through, the more energy you're going to get, which makes sense because each charge that goes through loses a certain amount of energy. So the more charges you send through, the more energy you're going to lose, the bigger voltage drop you'll have. And also, the more resistance that you encounter, the more energy it's going to take to get past that, and therefore the more drop in voltage you're going to have. Okay, to measure voltage and current, you can use electrical multimeters, which are either a voltmeter to measure voltage or an ammeter to measure current. But the way that you measure them is really, really important, and we're going to be doing a lab on this, so pay particular attention to how to connect them, because if you connect them wrong, you won't be able to get valid data. So voltage is measured across, okay? So you can say the voltage across something is something something volts. In order to measure the voltage across, you need to put one probe on one side and the other probe on the other side, and what it's measuring is actually the delta V between the two tips. Okay, so if you put both tips on the same side, you're going to get a delta V of 0 because they have the same voltage on this side and they have the same voltage on the other side. It's only across it that they lose voltage, aka lose energy, and that you'll be able to measure a delta V. Okay, if you get a negative value, it just means your two ends are on the wrong side, so that you're they have a black and a red end. You should put the black end at the lower voltage and the red end at the higher voltage in order to get a positive reading. But if you switch them again, it will just change the sign, so typically it doesn't matter which orientation you use because the numerical value will be the same. Okay, so voltage across things, you connect it in what's called parallel, because this and this are essentially parallel. Then to measure current, this is the amount of charges traveling through something. If you want to get the current traveling through something, you have to make the charge itself travel through your device. The way that you do that is by connecting it in what's called series, so it's just in a row. So what would typically happen, maybe you have your resistor and you've got a wire like this. What will happen is you need to break that apart so that now you have a resistor, and now that there's it's broken apart right here, where you actually have to disconnect something. Then you put your ammeter and you put the two ends of the ammeter here and here, so that the current has to flow this way through the ammeter and then back through. So it can't get from here to here without going through. So this is called connected in series, in line with or in series with the resistor. It can come before or after, it doesn't matter. So a lot of students, even though we've gone over it many times, they still think that in the resistor some current is lost. And so if you measure the current afterward, it'll be lower than if you measure the current before. But remember, what's being used up in the resistor is energy, not current. Current is just the flow of electrons. So the number of electrons coming in has to equal the number of electrons coming out. The electrons are not being given off by the light bulb or the resistor. They're just simply passing through it and depositing energy, basically, is what's happening. So the current after will equal the current before. There's an analogy I like to think about when I'm teaching this that hopefully will help you because it helps me remember it. I think of the electrons as mailmen, and I think of the mail that a mailman would carry as energy. So to me, the mailman is running, from here to here, and he drops off his mail at all these different spots along the way. And so the number of mailmen coming out has to equal the number of mailmen coming in. But what they did is they dropped off all their mail. So when the electron passes through, the current coming out is the same, but it has less energy. It's dropped off its energy. And that, to me, makes sense, or helps me think about it. Okay. So now that we're talking about energy and power, we can see how much energy is actually used up when the electrons or charges pass through a resistor. So we previously said it takes energy for charges to move through a resistor. How much does it take? Since when you have a circuit that's operating, the charge is flowing continuously, it doesn't make sense to ask about a total amount of energy. Instead, you want to ask about an energy per unit of time, which, if you recall from a long time ago, is a definition of power. So power is how much energy is being spent per unit of time. Typically, this is going to be joules per second, which is watts. Okay, so we'll find out how much power is delivered. If we plug in energy as Q delta V, because each individual charge that passes through some voltage difference is going to gain or lose a certain amount of potential energy. So Q delta V divided by T, because it's divided by time right here, we can group the Q over T, which is the amount of charges per second. That's the definition of current. So this energy per time becomes current times change in voltage. So this formula is called PIV. Ohm's law is called VIR, by the way. So we have PIV and VIR, just as a mnemonic to memorize them, PIVR. Anyway, the amount of power dissipated, or energy given off per unit time, is proportional to the current and the voltage. This, I think, also should make sense. If you have more current passing through something, it's going to give off more energy, or take more energy to do that. And if you have a bigger potential difference, a bigger voltage drop, it's going to take more energy. So let's think about water on a waterfall. This is a really good example of water on a waterfall. The more water you have going off, and the higher the cliff that it's going off of, the more energy is going to be deposited per unit time, or converted, say, from potential energy to kinetic or thermal when it hits the ground. So, you know, actually, the more I think about that, a waterfall is a pretty darn good example of a resistor. You've got a certain amount of water going off, and a certain height that it's traveling. Remember, voltage is kind of the analogy to height. So a difference in voltage, when charges fall from high voltage to low voltage, they give off energy. Just like when water falls from high altitude to low altitude, it loses potential energy. And then the waterfall, when the water hits the ground, it's back to the same velocity that it started with. So really where that energy is going is thermal energy. So the water at the bottom of a large waterfall should be slightly warmer than the water at the top. I mean, not very much that you would notice it on a small waterfall, but that's what's happening, I guess. Okay, so specifically for resistors, sorry, I got distracted there. Specifically for resistors, we have the Ohm's law here, V equals IR. So if you combine PIV and VIR, you can get two other formulations here. So you can say that the energy dissipated in a resistor per unit time, which is the power, is I squared R, or it's also V squared divided by R. So depending whether you know the current or whether you know the voltage on the resistor, you can figure out how much power is dissipated. And you can see right here that if you increase the current, it's going to be a lot more energy dissipated. Whereas if you increase the voltage, it seems like there's going to be a lot more energy dissipated. But actually, this is tricky to explain. Let me think about how to explain it. So, okay, let me use power lines as an example of when these formulas can be valuable. So if you have this formula PIV, P equals IV, the power company has to deliver a certain amount of power to you to keep your house functioning. So say the power needed is constant, then if you increase the voltage, you will decrease the current. Okay? And so if you increase the voltage by, say, a factor of 10, then you decrease the current by a factor of 10. And so while the total power delivered to your house, say, for example, is going to be the same, the power lost due to the resistance in the wires themselves will decrease because the current is being decreased. So there's two types of power that you can kind of think about. The power delivered, which is current times voltage coming into your house, for example. Then there's also the power lost in the wires themselves, because all wires have a little bit of resistance. And so you know, if you had a big thick metal cable that's a few feet long, its resistance would be negligible. But when you have it 10 miles long going from the power plant to your house, then suddenly that resistance becomes really important. And if you had a lot of current traveling through that resistance in the wire itself, you would lose a lot of energy just getting from the energy from the power plant to your house. But if you increase the voltage and therefore decrease the current, then the current traveling through that resistance is really, really, really small, and then you square a small number, it gets even smaller. And so the energy that you lose in the resistance of the wires is very small. And so then you might be wondering, well, how do you change the voltage or the current? And you can do that using transformers. So as you see on power lines, they've got transformer boxes. You can step up the voltage to really, really high voltage, and then transmit the energy at high voltage, and then step down the voltage back down to like 120 volts for your house, for example, and then feed the energy into your house that way. So I have some transformers, and we can do a lab on that as well. Okay, here's a quick sample problem. What is the resistance of a 1500 watt, 120 volt hairdryer? So you plug your hairdryer into the wall. It says on the side of it that it uses 1500 watts. You want to know what's the resistance inside of there, because all a hairdryer is a fan behind a resistor. So the resistor gets really hot, and then when the fan blows hot air out the end. Okay, so hairdryer 120 volts. So we got V equals 120 volts. Power equals 1500 watts. So we don't know the resistance, and we also don't know the current. So we could use PIV. We could use VER. Those are our two basic ones. But we also have P equals I squared R, and P equals V squared divided by R. Personally, I just have these two memorized, and I can get these from these whenever I need them. But if you want to memorize all of them, you can. What we really are asked for is what is the resistance and what is the current. We need to find both. So you can do them in whatever order you want. We know V and P. We know V and P. So I'm going to start with this one, and I'm going to find the current. So current equals P over V, which is 1500 divided by 120. So cancel one of the zeros, and you get that the current is 15 over 12 reduces to 5 over 4, which is 125 amps. That is ridiculous. Sorry. That zero cancels with that zero. It's not 125, it's 12.5. Okay, that's much better. Typically, a house has a 20 amp circuit breaker. So if you try to draw more than 20 amps, your circuits will shut down. I'm sure you've had that happen to you if you plug too many things in at once. So I knew that getting an answer of 125 was too high, so I apologize. 12.5 amps. And what is the resistance? Okay, we've got V equals IR, so we can use that to get that R equals, sorry, that's an equal sign. Resistance is voltage divided by current. Voltage was 120. Current was 12.5. So the resistance is something around 120 over 12 is about 10 ohms, something like that. So low resistance allows you to have a high current, which allows you to dissipate a lot of power, which is what you want for a hairdryer because you want it to get really hot, so that way when the fan blows, it'll be warm air. Okay, we're almost done. Energy versus power. So a lot of times you talk about the power company, but what they're really selling you is not power. What they're really selling you is total amount of energy. So they don't care if you use a whole bunch for a short amount of time or a little bit all the time. What they care about is the total amount of energy that you use, and that's typically called the kilowatt-hour. Okay, so kilowatts are units of power, and hours are units of time. And if you multiply power times time, you get energy. So energy is power times time. So if you plug in what is 1 kilowatt in power, a kilowatt is 1,000 watts. And then if you plug in for time, what is 1 hour? An hour is 3,600 seconds. If you remember that a watt is a joule per second, seconds cancel, and you're left with joules. So 1,000 times 3,600 is 3.6 million. So 1 kilowatt hour is 3.6 million joules. And you should maybe ask your parents if you can see their power bill. I'd be curious to know how many kilowatt hours your families use in a month, which is, a typical thing. I know that the electric company, they allow certain amounts of kilowatt hours per house, and it's based on factors like where you live and how big your house is and if you have a pool or not or things like that. But the amount of money that they charge you changes depending on how much energy you use. So you have what's called a baseline amount. if you use that much energy or less, you get charged a certain amount per kilowatt hour. But if you go above that, you get charged a much higher rate. And so, the idea is that you want to have people practice energy conservation whenever possible. So, things like leaving the lights on. If you have a 60-watt light bulb and you accidentally leave it on overnight, you're looking at 60 watts times 12 hours, and 12 hours times 60 minutes, and 60 minutes times 60 seconds. 60 times 60 times 60 times 12 is actually quite a lot of joules, right? So it's using a lot of energy. And so what you want to do is you want to be conscientious and try to be energy efficient, use energy efficient light bulbs, star appliances that are rated energy efficient, etc. Cool. All right, recap of important stuff, and then we'll wrap it up. Current, variable I, is the total charge passing per time. It's conserved, which means the amount in is equal to the amount out. It never gets used up. The amount coming in equals the amount coming out. That's really, really important to remember. Other thing is the voltage equals current times resistance. This is Ohm's law. You should probably remember the name because it's referred to a lot. Ohm's law. Ohms are the units of resistance, which is the R variable. And delta V is proportional to the energy change, remember? So it takes energy to travel through a resistor. And delta V equals IR, Ver. The resistance opposes the flow of charge. I'll mention here, I probably should have mentioned this earlier, there's this other thing called conductivity. Conductivity is the inverse of resistance. So conductivity is proportional to 1 over resistivity. So if something has a high resistivity, it has a low conductivity. If something has a low resistance, it'll have a high conductivity. So they're just two sides of the same coin. If you know one, then you know the other one. They're inverses of each other. Last thing is power dissipated equals I delta V, and then there's two other formulas for it. But essentially, if you know Ver and Piv, Piv and Ver, Piv and Ver, Piv and Ver, and the definition of what charge is and what current is, then you should be in good shape for this chapter. The questions should be pretty basic about energy dissipated or resistance of some kind of object or current traveling through it. All right, we'll get to circuits a lot more in the next chapter, but I just want to remind you, battery looks like this, resistor looks like this, and you can connect them up with a wire. So if it says you've got a circuit with, say, 2 resistors, you can label R1, R2, and V sub battery or something like that, So a battery with 2 things plugged into it might look something like this. All right, happy hunting. Good luck on your homework.